Welcome to mirrors. We are going to be describing the types of mirrors. We're going to describe the types of images formed by mirrors, differentiate between those types, that's virtual and real, use the mirror equation to relate the focal length, radius, distance to the object, and image and orientation and type of image. Now, images are important to everybody, and they're extremely important in physics. Images are crucial to a wide variety of fields and industries ranging from entertainment, security, and medicine. In this chapter, we will define and classify images and then classify this in several basic ways in which they can be produced by mirrors. Later, we'll do the same thing for lenses. And we will also use the ray model for light, in which we assume the light travels in straight lines, that is, light rays, that represent very narrow beams of light. Now, an image is basically just the reproduction of an object via light. If the image can form on a surface, it's a real image. And it can exist even if there's no observer present. So in other words, if this lecture were being viewed on a screen in the classroom, you see the image on the screen, it's a real image. So the light actually passes through a real image. If you put a view screen at the image's location, actual image would form on the screen, and the light rays form the image. If the image requires a visual system of an observer, then it is a virtual image. A reflection in an ordinary plain flat mirror is a virtual image. No light actually passes through this virtual image. If you put the view screen at the image's location, no image would form on the screen. So you put your head behind the mirror, there isn't anything there. Our brains instead form the image from the projection or extension of the imaginary light rays. Mirrors and lenses can form both real and virtual images. Okay, the easiest type of mirror is a flat mirror, otherwise known as a plane mirror. Now, you take any 4-year-old child, they know that there's nothing behind the mirror. Babies don't. Babies think that baby in the mirror is real. Kittens do the same thing. You watch a kitten dance up to a mirror, he's all fluffed up and he's attacking the kitten in the mirror. Later, when he gets a little older, he's running around behind the mirror. It doesn't smell like anything back there. There's nothing back there. Where's the kitten gone? And he very quickly gets bored with it and stops looking for it. What the kitten or the baby saw is a virtual image. What the 4-year-old and the cat knows is it is not real. So if you put a view screen behind the mirror, nothing shows. We can locate the image by ray tracing and extension. And of course, that is these dashed lines in these figures. Those are the extensions. And we're going to use geometry. So we have several triangles here. We have PQR, and this triangle is the same type, same size and everything as P prime QR. So side PQ is the same as side P prime Q. So this distance is the same as this. Side QR is the same for both triangles. And since this part is parallel to that, H equals H prime. Okay, this gives us the mirror equation and the magnification, which will be on the next slide. Virtual images are almost always upright. In other words, they have the same vertical orientation as the object. So here you go, that's upright, so is this. Real images are usually inverted. In other words, if this were a real image, it'd be on this side of the mirror and it'd be upside down. We'll talk more about that later. Okay, so triangle PQR is equal to this triangle, P prime QR. So side PQ is equal to side PQ. And also this height here is equal to that height. So this gives us the flat mirror equation. The distance between the mirror surface and the object equals the distance between the mirror surface and the image. So distance to the object is equal to distance to the image. You always measure that distance relative to the mirror surface. We're going to put absolute value signs on there because we'll later encounter a sign convention. DO, distance to the object equals distance to the image, or P, that's the distance to the object equals the distance to the image. You might also see I used for image. Each text uses different symbols, unfortunately, and I'm sure this are not all the ones that I've seen out there. There are many of them. You just have to be careful. Now, the object distance is positive because it's in front of the mirror. The image distance is negative because it's behind the mirror. The absolute value signs are there to account for the sign convention, and that says that distance for images formed behind the reflecting surface are negative. Now, the size of the image, in this case, equals the size of the object. And since magnification is a ratio of the size of the image to the size of the object, magnification is 1. The image is upright, that is a positive H prime. It's virtual, it's behind the mirror. The negative sign on the image distance would be that, and it's the same size of the object. So as I mentioned before, H prime over H is the magnification, that equals 1. Now, ray tracing can be used to determine the orientation and location of an image. And any extended object can be considered to be composed of many single point sources of light. That's Huygens' principle. Each point source of light in the extended object can be mapped to a point on the image, and that will form the image. The angle of incidence for a mirror is going to be equal to angle of reflection. We can still use that. We can simplify things. We're only going to consider 2 points, such as the top and the bottom. Now, we usually draw an object as an arrow. We almost always put the upright arrow with the base of the arrow along the central axis of the mirror. That's a line that runs through the center of the mirror, perpendicular to the mirror surface. And then the object is usually set as an upright arrow with its height, a scale factor of the actual height. Okay, so and then we place this along the central axis here. We know that this is going to, the image is, the butt of the arrow is going to be on that same axis. We don't know for sure how far back behind or in front of the mirror. We know it's somewhere along that central axis. And then we use ray tracing from the tip. If we do get 2 rays or 2 extensions going through a single point, then we know that that's where the tip of the arrow is. We just draw the arrow between the 2 things and we use the arrowhead at the tip. Okay, so this is what you have to do for virtual images. You have to use ray extensions, and we will be using ray tracing on mirrors and lenses. Now, a spherical mirror is basically just a small section of a spherical surface. A flat mirror is basically a one type of mirror. It's a mirror where the radius is infinite. A concave mirror looks like a cave when you look into it, and it's like the side of the spoon that scoops up your soup. In that case, the radius of the mirror is positive. Here's the center of curvature. The radius, of course, is that distance here. And of course, for a concave mirror, R is positive. In other words, the center of curvature is on the shiny side of the mirror. It's the side the light would come from. On this mirror here, this is the shiny side of the mirror. This is the side the light would come from. This is the dark side of the mirror. Notice the central is now a distance R behind the mirror surface. And there are other shape possibilities, such as parabolic. Okay, C is the center of curvature. It's the center of a sphere of which the mirror surface is a small part. It is located at distance positive R in front of, as the same size as the object of a concave mirror. It is located at distance minus R in the back of a convex mirror. The magnitude of R is the radius of the sphere, and for a plane mirror, a flat mirror, R is just an equal infinity. Now, the field of view is how much an observer can see in the mirror. For a concave mirror, the field of view is smaller than that for the equivalent situation in a plane mirror. For a convex mirror, you have a wider field of view than in the equivalent plane mirror. This is why security mirrors are convex mirrors, because it sort of lets you look in a wider field of view than you otherwise would. The central axis is an imaginary line. It runs through the center of curvature of the mirror, through the center of the mirror's surface, little c, ditto for here. And when we ray trace, we place the bottom of the object on the central axis. So that means that the bottom of the image will form somewhere along the central axis. And central axis almost always contains the focal point. We'll talk about that in the next slide. The focal point is given the symbol F, and otherwise known as the focus. It's the point at which, if you have parallel light rays coming in, it's a point at which they will bounce off the mirror and come together at a certain point. That distance from that point to here along the central axis is the focal length of the mirror, little f. And we find this by ray tracing, and we can also use the formulas. We'll do that later. F is, of course, the distance on the central axis between the mirror surface and the focus, and there's a radius-focus relationship for spherical mirrors, 2F equals R. For a convex mirror, we have to use extensions. We have the parallel light rays coming in, and we use angle of incidence equals angle reflection around a normal that's perpendicular to the surface at this point, and then we ray trace or draw extensions back from this reflected ray here and from that one. And where they intersect gives us the focal length of the mirror. And of course, this one would be negative, and so would R. Okay, so a concave mirror. Concave mirror curves inward when you look at it. It's like the side of the spoon that you scoop the cereal out of. In this case, the center of curvature C is in front of the mirror, and R is positive. The focal length will be in front of the mirror, so F is positive. The image is larger and further away from the mirror than the object, and concave mirrors can form virtual images as well as real images. The real image here is C here, and this is when the object is further away from the mirror than the focal point. So it's outside the focal point. It can also form a virtual image, which is here. This happens when you have the object inside the focal length of the mirror. So in other words, it's closer to the mirror surface than the focal point is. Real images will be inverted and form on the front of the mirror, right over here. Virtual images are upright, and they will be behind the mirror. So in this case, P is negative. In that case, P is positive. For a concave mirror, the field of view in a concave mirror is less than it would be for a plane mirror. Now, a convex mirror curves outward as you look at it. It's sort of like it's the back side of the spoon. The side you can't eat off of. C will then be behind the mirror. R is then negative. The focal point will be behind the mirror, so F is also negative. the image is smaller and closer to the mirror than the object, it will only form a virtual image upright and behind the mirror. So P is negative. The field of view will be larger than it otherwise would be for a plane mirror. And this is why we use these in security mirrors and the passenger side mirror. Objects are closer than they appear. Why is that so? Our brains will say this truck is big. It's a large truck. And we know that it should appear a certain size at a certain distance. If it appears smaller than it should be, our brain says it's further away. So you have to be careful when you use these mirrors. They're good because they allow you to see off to the sides here because their field of view is wide. Spherical mirrors, you want to locate the focus. The easiest way to locate the focus is with light rays that are parallel to the central axis. So you send parallel rays into a concave mirror, and the parallel rays are coming in parallel central axis. They will obey the angle reflection equals angle of incidence equation, and they will pass through a common point F at a distance little f. This is a positive quantity from the mirror. For a convex mirror, you have to use the ray extensions. Here they have the rays coming in, they're parallel to the central axis, and they bounce off angle of incidence equal angle of reflection around that normal to the mirror at that plane, so at that surface at that point. And we have to use the extension here. We take these extension back from this ray and that ray. They'll intersect through the focal point, okay? And F will be negative, and so is R. For mirrors of both types, the focal length is related to the radius of the curvature in the mirror by F equals 1/2 R, where R and F are positive for concave mirrors and negative for convex mirrors. Okay, now the mirror equation. The mirror equation relates an object's distance P, the mirror's focal length F, and the radius of curvature R, and the distance to the image. And it is 1/P plus 1/I equals 1/F, and that also equals 2/R. Now, this will be useful for the lens too. This one is only for mirrors. Sign convention. Anything in front of the mirror, the shiny side of the mirror is positive. Anything behind the mirror, dull side of the mirror is negative. Distance to the object is always positive, unless you've got something weird. Okay, so concave mirrors, F and R are positive, but I is negative. In other words, it's virtual. If P is less than F. If P equals F, then I equals infinity. So it actually comes out of parallel lines, and that forms at infinity. If P is greater than F, then I is positive, and it's real. Here's the real image. It's upside down. It's on the same side of the mirror as the object, so it's real. Here is the virtual image. It's right side up. It's behind the mirror. Okay, now mirrors can magnify things too. This magnitude of the lateral magnification M of an object is the ratio of the image height H prime to the object height. And magnification also equals minus I/P, where I is the distance to the image and P is the distance to the object. And distances are always measured relative to the mirror surface, by the way. Now, we can ray trace for concave mirrors. In the old days, this is how we literally did this. Now we have calculators. We usually use the lens equation or the mirror equation to do this. Now, a ray that is initially parallel to the central axis, so that's this one, will reflect through the focal point F. That's this ray number 1 here. A ray that reflects from the mirror after passing through the focal point will emerge parallel to the central axis. That's that reversibility thing we talked about before. A ray that reflects through the center of curvature will pass back on itself. So it just returns the way it came. A ray that reflects from the mirror at point C, which is right here, will reflect symmetrically about that axis. So this angle here will equal that angle there. And here's the ray coming out. The intersection of any two rays from the same point on the object determines the location of that point on the image. Two different points will determine the location of the image. We always draw the butt of the arrow on the central axis. The butt of the arrow will be somewhere along the central axis here. And then we use ray tracing. You just need 2 rays to determine what orientation and size is this. Convex mirrors are a little bit more complicated because you need ray extensions for everything. So in this case, a ray that is initially parallel to the central axis reflect along a line whose extension passes through the focal point behind the mirror. Now remember, it's behind the mirror. A ray whose extension, that is a dashed line that goes through the focal point, if you extended this, they didn't show this. If you extended this line right here, it would go through the focal point. So that means it's going to emerge parallel to the central axis. A ray that will reflect from the mirror after virtually passing through the center of curvature will return along itself. That's ray 3. A ray that reflects from the mirror at point C, the center of the mirror, will reflect symmetrically about that axis. And that's this ray 4. Any 2 rays from the same point on the object will determine the location of the point on the image. You just need 2 different points to determine the location of the image. So basically, you put the butt of the arrow on the central axis. So you know that butt's going to be located somewhere along the central axis. Then you draw the tip, and then you do ray tracing. You need two rays where they intersect to form the image. Okay, as an example, a tarantula of height h sits cautiously before a spherical mirror whose focal length has an absolute value of 40 centimeters. The image of this tarantula produced by the mirror has the same orientation as tarantula, has an height h prime of 0.20 h, so it's about 1/5 the height of the object. Is the image real or virtual? Is it on the same side of the mirror as the tarantula or the opposite side? Is the mirror concave or convex, and what is its focal length sign included? Okay, the physics of this is spherical mirrors. We're going to expect that the image is upright, same orientation as the object. And it should be virtual and on the opposite side. The image height is less than the object height, so the mirror is convex. And the focal length should be negative, so that's how you can tell. Concave mirrors don't usually produce a smaller image. So then we write down everything we know. We know the focal length is 40 centimeters. We're going to have to put a negative sign in front of that. We know that the image height is 20% of the height of the object. The image orientation is the same as the object. We need to know the type and location of the image, type of mirror, and what's the focal length. And of course, we drew this because we didn't know which type of mirror it is. Is it concave or convex? And here's the tarantula. We have some formulas. Magnitude of m equals h prime over h, or m equals I over p, and we have 1 over p plus 1 over I equals 1 over f. So now we can start substituting in here. We can solve this. I equals minus h prime over h times p. We have 1 over f equals 1 over p plus 1 over I. We can substitute in. It becomes 1 over p minus h over h prime times p. 1 over f will then be h prime divided by h prime p minus h over h prime p. Pull this out, h prime minus h over h prime p. So f is h prime p over h prime minus h. And you can copy this down in your notes. It might be useful. It's okay. Okay, the orientation's the same. The image must be a virtual image. They said it was upright. And it's going to be on the opposite side of the mirror, so I is going to be negative, and so will the focal length. Focal length is going to be minus 40 centimeters. So now it just becomes a matter of just plugging numbers in. We know that f equals h prime p over h prime minus h. We plug in 0.20 h for h prime, ditto for this. Cancel out some terms we don't need. And we wind up that f is minus p over 4. So f is minus 40 centimeters for a p that's greater than 0. Since f is less than 0, the mirror is convex as expected. Now, spherical aberration occurs when the rays don't come to a sharp focus. So rays coming from a distant object are essentially parallel, and we usually set it up so it's parallel to central axis. Spherical aberration occurs when the parallel rays hit a spherical mirror and they don't always converge at exactly the same place. In other words, some of them may come to focus here. Here's where they come to focus from this end. Don't come to the focus the same place. This is very annoying. It's blurry. It might be a ring, blurry ring. It's more likely to happen when the mirror is highly curved. The radius of curvature is small relative to the size of the mirror or the part of the mirror that's being used. It's much less of a problem when the radius of curvature is large relative to the side of the mirror. Then the parallel incoming rays will focus tightly at one spot. You can also use a parabolic mirror instead of a spherical one. So in other words, spherical ones suffer from spherical aberration. Parabolic mirrors do not, but they're harder and more expensive to manufacture. You're standing in front of a mirror at point P, as shown. There's a light bulb behind the screen that you cannot see directly. As you look in the mirror, where does the image of the light bulb appear? Okay, so it's going to appear at point C. So you draw a ray from the bulb at D, here to D, and then to P, because you know it's going to bounce off. The angle of incidence equals the angle of reflection. You extend the ray PD to C, and then draw a line from B to C to E. The image will form right here at C, where the lines intersect. A ball is held 1.5 meters in front of a plane mirror. How far is the image of the ball from the ball itself? Now, this is a trick question. They're not asking the distance between the ball and the mirror surface, or the image in the mirror surface. They're asking the distance between the ball and its image. So I will be P. It's a plane mirror. And these distances are measured relative to the surface of the mirror. So then the distance between the image and the ball will be twice that. Okay, so in other words, the ball is on one side of the mirror, the image is on the other, an equal distance behind the mirror. So that will be 3 meters. Daniel walks directly toward a plane mirror at a speed of 0.25 meters per second. Determine the speed of the image relative to him. This is the same question we had before. If he's walking at 0.25 meters per second, his image is approaching him at twice that speed, or 0.50 meters per second. The distance between Daniel and the image he sees is 2p, and that's I plus p. Assume he walks toward the mirror and a distance p and time t relative to the mirror. Speed is distance divided by time. If the speed relative to the mirror is b equals p over t, his image is moving toward him at a speed of v of I over t. Both of these are relative to the surface of the mirror, but relative to him, his image is moving at 2p over t, or twice as fast. Which of the following statements concerning a convex mirror is or are true? So basically what we've got, only one of these is true. The image will be closer to the mirror than one produced by a plane mirror in its place. So I will be less than p. Such mirrors are always a portion of a large sphere. No, you can grind it in a parabolic shape or any other shape you want. The image formed by a mirror is sometimes a real image. Convex mirrors never form a real image. They only form virtual images. The image will be larger than one produced by a plane mirror. False. Convex mirrors images are always smaller than the one produced by a plane mirror. The image will always be inverted relative to the object. That's only true for real images. All of these are virtual images. They're always going to be upright. Now this one, I want you to do at home. Okay, and I will post online, or have posted online, a handout that you can download and print out. And you can bring this with you. You don't have to recopy the whole thing, just fill in the table. And you want to fill in here. You can bring this with you to tests, and it can assist you on tests. So this is perfectly legal to bring with you to a test. Okay, so you're sitting in the back row of the classroom. Your instructor is standing in front of the room with a large convex spherical mirror. What do you see in the mirror as your instructor walks from the front of the room to your location? So we're going to put some likely numbers in and try them. Okay, so what you're going to do is you're going to do this, plug in the numbers that I give you. Okay, here they are. And what you want to do is you want a convex mirror. F is 1 meter. Make it easy. Focal length of 1 meter. The first thing you want to do is you want to determine the sign on F. It's a convex mirror. Be careful with that. Now, you're going to figure out using, here's some equations. The magnification is F divided by F minus P, and you can use these in your notes. And I is minus P times M. M is the magnification. P is the distance to the object. I is the distance to the image. F, of course, is the focal length. Okay, and you plug in magnification. We'll actually do the equation. Here you're given enough information to do it. Get the magnification for all these different values. Get the image distance for all these different values. Get the size. Is it larger or smaller? And then you're going to figure out the orientation, right side up or upside down. The sign will tell you that. And then is it virtual or real? Is it behind or in front of the mirror? Okay, now you won't know this yet, but the kind of lens that a convex mirror is equivalent to is the concave lens. For a mirror is a real image on the same side of the light source. You might want to look that up or figure it out. For a lens, and of course, you're going to find out the lens is on the opposite side. You'll do the same thing with a concave mirror. Okay, you will find out, you will see the image right side up. It gets larger as the mirror approaches. It is a convex mirror, so it's never going to be as big as you are. Same thing, but now we're doing this for a concave mirror. You'll see your image initially inverted and then right side up. It gets larger as the mirror approaches. While shopping in a grocery store, you look up at a convex security mirror. You notice that your image is about 1/4 of your height. By estimating your distance to be 2 meters in front of the mirror, determine the focal length of the mirror. It is 0.67 meters. Magnification is h prime over h, or minus I over p, and we were given that 0.25. P is 2 meters. I will be minus 0.25 times p, or minus 0.5 meters. 1 over I plus 1 over p equals 1 over f, so we plug in what we know. We find the focal length is negative 0.667 meters. We kind of expected that because it's a security mirror. Consider the strange device pictured above. At the center of curvature of a concave spherical mirror, there is placed a light bulb. Actually, there are 2 light bulbs. The focal length of the mirror is 5 centimeters. The device has 2 bulbs. The lower one happens to be burned out. What will happen when the upper light bulb is turned on? It's kind of a weird little device. Okay, actually what's going to happen is the lit bulb's image is going to appear inverted at the same location as the unlit bulb, so the unlit bulb will look like it's turned on. I guess you could use this for like security or a lighthouse. Okay, so F is R over 2 and P equals R, because they told us it would be put at the center of curvature. So 1 over P plus 1 over I will equal 1 over F. So I will equal 1 divided by the inverse of F minus the inverse of P. And we can rewrite that as 1 divided by the quantity 2 over R minus 1 over R. I is greater than 0, so it's going to reel in inverted and located at the same distance from the mirror as the object. Okay, thank you very much.